All right. Thank you everyone for coming. So today we have the pleasure of listening to Dante Bonolis from University of Basel, and he's going to speak on the density of rational points on some quadric bundle threefolds. Please, Dante.
Okay, thanks, Ramon, for giving me the chance of talking here today. And whatever I'm going to say is a joint work with Tim Browning and Zhizhong Huang. Yeah, so in this talk, we're gonna basically try to prove some instance of Manin conjecture for some Fano threefold over Q. I mean, yeah, now I'm just gonna say the setting. At the end of the day, we're gonna really work with some very concrete examples. So, I mean, even if you know what is a Fano threefold, it's fine. Just okay. So we start with X is going to be from now on a Fano threefold, and since we are trying to basically establish a quantitative result, we need a lot of rational points on it. So the first requirement would be that the rational points are Zariski dense in X, and moreover, here capital H is going to always denotes the anti-canonical height function over our Fano variety X. Again, I mean, it's going to be very, very explicit later on, so no worries about this. Okay, before to state what is called Manin-Peyre conjecture, I want to recall the definition of a tint set. So basically, we consider a subset of the rational point of X. And we say that this Z is going to be a tint set if it's the finite union of two set kind of set. The first option is to take a closed subset of X and then take the rational point on it. And this usually is also called type 1 tint set. And the other option instead is to basically consider a dominant morphism of degree larger than 1 of an irreducible variety in X, and then take the image of the rational point over Y. And this usually is defined to be, it's also called a type 2 tint set. Okay, so now we're ready to state the Manin-Peyre conjecture. So basically,
just bother you. Can you say what's a dominant morphism? Sorry.
That the image is dense in X. Yeah. So here we have the Manin-Peyre conjecture. There exists basically so we have our Fano threefold X. I mean, it's actually true for any Fano variety, and we can find there exists a tint set in X such that I mean, if you count all the rational point in X away from Z of height at most B, this should grow asymptotically as a constant, which depends on the variety X times B time a power of the log, which is governed by the pK group of X. And moreover, like, I mean, basically Manin, it just predicted the order of magnitude B log B to the power rho minus 1. And Peyre gave basically an explicit conjecture about the constant. And okay, there is this alpha beta. I mean, the things. It's very easy to understand what these omega px are. These are basically the density, the p-adic density of the variety X. Okay, so before going on, let's try to see. What is known about general threefolds. There is a theorem by Manin in the 90s. Basically, if you take any smooth Fano threefold over Q, you can always find a number field extension of Q, such as if you try to count instead of the rational point, the K point, up to of certain height B, you have a lower bound of the size of B. And actually there are also like upper bounds, basically Tanimoto and Salberger, they prove upper bound of the form b to the power 1 plus epsilon. So, which is so like once you remove the like something set which concentrate too many rational points. Okay, so today we're going to focus on the case when rho is equal to 2. And I mean, the first things I want to recall like is that there is a classification of such threefold, and it turns out that I mean up to an isomorphism over Q bar, there exists 36 different Fano threefold with Picard rank equal to 2. And here it's, I mean, I don't want to write down all the list, but you can list all of them from 1 to 36. This list it's made according some geometric invariant. I don't want to enter in detail with. I just want to point out that this is it works a bit like this list works a bit like Del Pezzo surfaces. Like, you know, we know that for this first Del Pezzo surfaces we have just 9 different degree, and we know that the smaller is the degree, the harder the arithmetic of the surface is. For example, if you take a Del Pezzo surface of degree 9, this is just a projective space, so it's quite easy. Instead, like if you reach up to the level the Del Pezzo of degree 1, it's a rather complicated object, and there are a lot of if you try to do things quantitative, basically nothing is known about it. And here is gonna kind of work the same. So the earlier these varieties appear in the list, the harder they get. So here I want just to see what instances of and give some example of variety which are known. So the first 3 case, okay, let me try to get the right color here. I guess it's, no, probably it's not. Okay, let's try. So the number 36, 35, 34, and 33, they were covered by Batirev and Chinkel in 98. And, oh, wow. Wait. Okay, I picked the pencil, so, oh, whatever, wait. Batirev and Chinkel in 98. This is like in the set of the toric variety. Whatever they are. The only things I want to point out that like what is this 36 threefold? This is given by P2 cross P1. So you see this is really something which is one expect to be quite easily detected. Then in 2008, Spencer covered cover number 32, and this is something called bidegree 1,1 in P2 cross P2, and basically this is just the solution of the equation xi yi from y from 1 to 3, and basically this is something that, like, you know, it's degree 1 in xi and degree 1 in yi. Then if we go on with the list, number 31, 33, and 28 were covered by Chamberlain and Chinkel, and something's called equivariant. So these are, like, I don't give example, the equivariant compactification of A3. And finally, another instance for which is known is given by the number 29 in the list, which is also quite a recent work by Blumer, Bruden, Derenthal, and Gagliardi last year, and they basically cover some things called spherical variety, and in this, I mean, number 29 is one of them, and this is just a blow up of a conic, or along a conic of a quartic in P4. And so today, which I mark in red, is gonna cover the number 25 in the list. And this is, it's basically, we can see this as a blow up along a genus 1 one curve of the projective space. And this is actually gonna have a very, very explicit description now. So let's start. So this is now, it's covering.
A question. So
Yeah.
all these results are the same quality. They all prove the Manin's conjecture.
This is about
Okay.
Manin conjecture. Yes.
Okay.
Yes. So we start like considering genus one curves. Basically, this is gonna be the intersection of two quadrics. And I mean, we're gonna consider like two quadrics, so Q1 and Q2 now are gonna be two diagonal quadrics. In for variable. Okay, I mean, we also require E to be smooth. So it means that basically the intersection between these two quadrics is smooth. So what is, I mean, now we're gonna give like a very explicit description of our Fano threefold. X is gonna be the following. So basically, we are gonna look for point in the cross product P1 cross P3. Such that the following equation hold. You take Q1 y times x1, and this needs to be equal to Q2 y times x2. Here I use the convention, and this guy is x1 x2, and this is okay. Actually, I mean, also it's something we're going to use very often. Basically, P1 cross P3 as a, I mean, it comes with, I mean, it's a fiber product, it's a cross product, so you have like basically two fibration, 1 over P1 and 1 over P3. And the thing is that our variety is going to heritage this double fibration. I mean, and actually we can rewrite the following, the equation defining X in the following way. I mean, basically, if we write the quadric as AI yi squared from 1 to 4, and then we define they need to be diagonal. Then we can rewrite X. Basically, we can pair the coefficients of y1, pair the coefficient of y2, y3, and y4, and so we can basically rewrite as in the following way. You consider Lix, where here Lix is just okay. Okay, so here you see basically it's what I was talking about, that we have this kind of a double fibration. I mean, we have two possibilities. The first thing is we can fix y. If we fix y, we just get 1 point, right? Because we know that X needs to be a point in the projective space. So this equation here define the point X. Otherwise, we can do the other way around. We can basically fix y and then, sorry, we can fix X and then we get a quadric. And yeah, and then this is very visible in this equation because this is just basically a parametrized family of quadrics. Okay, so the next step is that, okay, this is our Fano variety. Before even start to talk about, like, try to count some things, we need to because Manin conjecture is about counting rational point away from a thin set. So we need to find the thin set we need to exclude. And there was like a paper by Elseans in 2011, And he gave the following suggestion. I'll try to motivate a bit. So the idea is that, like, when you want to exclude thin set are basically a subset of X, which are a concentration of rational point, like a too big concentration of rational point, which can mess up with your asymptotic. So the idea is, again, try to look at the way Elseans did his prediction was just looking at the vibration, and it was just like basically removing the let's say problematic fibers. So okay, let's start with the P2 fiber. So here we're fixing Y, and we are taking the P2 minus 1 Y, and I said that this is gonna be basically a point, but this is gonna be generically a point, because, you know, if you look this equation here again, I mean, it might be that Y is in the intersection of is in the intersection of the two quadrics, and if this happens, basically you can freely choose X1 and X2. So here there is the warning that if Y is in E, what we get is that the inverse image of Y is going to be a copy of P1. Oh, sorry, maybe. And this has too many points. And so, I mean, this is basically the first part of how I wrote here the thin set. This is actually a type 1 set. And instead, we can try to see on the other side, like what happened for the other vibration. The other vibration, we are basically fixing X, and we are just getting a quadric. But also here there is a problem, and the problem is that the quadrics can be what is called a split quadric, and the problem of the split quadric is that they have too many points, meaning that if the inverse of this point is a split quadric, basically any of this fiber is gonna contribute with a constant which depends on the point X times B log B, and this would be a problem because, you know, if we have too many of this point, then, I mean, this is gonna, I mean, already this B log B has the same order of magnitude of our the main term we want to prove. So I mean, if you have too many of this point, you might add up too many things. So basically, we need to exclude also this union here, and this turned out to be a type 2 set. Okay. I just want to conclude this part saying that actually there is a very, very concrete way to check whenever a quadric is split or not. And basically, if you have a quadric of this form, you know that this is a, sorry, maybe I can rewrite this a bit better. We know that basically this is a splitting quadric. If and only if the product of all these coefficients it's a square. So you see, basically what we will be need to remove are all these point X, such that because now, you know, our AI is going to be the evaluation of this linear format X. And basically, we need to remove this point in. I mean, this is actually is define an elliptic curve in a weighted projective space. So basically, we have given weight 2 to Z. So this is actually it's homogeneous when you give the weight 2 to Z, and this is going to be an elliptic curve. It might be that this. I mean, if you the rank of this elliptic curve is larger than 0. You might have like infinitely many points. That's why you actually need to remove all these points here. Okay, so here finally I can state the result with Zhizhong and team. So we start with 4 linear form, L1, L2, L3, L4, and we consider our like Fano threefold. Then we need to have these 4 assumptions. The first assumption is that these Li and Lj are not proportional if I is different by j. Then we have the assumption that the Li actually have like coprime coefficients. And finally, we also require that, so basically E is the intersection between the 2 quadrics, and we require this intersection as not real point. And if all these conditions are true, then we can prove like Manin-Peyre conjecture for this Fano threefold, where the constant is the one predicted by Peyre, and where actually the thin set we need to remove is the one predicted by Elsans. Here I want to make some remark. Okay, there is this condition 1 here, and this is a necessary condition because we want E to be smooth. Instead, these other 2 are not necessary. And I mean, actually, especially this one, it would be nicer not to have there. Actually, we had a strategy to like remove that, but the paper was already quite long, so we decided not to pursue it. But actually, I think this is, they're both just technical assumptions. It's just to make the argument much, much easier, and because it's already quite messy, and yeah. But anyway. Okay, but here, like, I try to give you an example to show that actually this is not an empty statement, that we can find actually an example of such a Fano threefold. Okay, here, okay, let me write Q1 y is gonna be equal to y1 square plus y3 square plus y4 square. And instead Q2 y is gonna be equal to y2 square plus 2y3 square plus 6y4 square. It's easy to see that E of R it's empty because if you require Q1 y to be 0, it follows that y1, y3, y4 they have to be equal to 0, and then this force also y2 to be equal to 0, just using the second equation. And moreover, actually, I want just to point out that if you try to write down the point which give you like a split curve, split quadric, this is going to be equal to x1 times x2 times x plus 2 plus x plus 6 x s2, and this actually is a rank 1 curve, right? Is a rank 1, so it means that basically we need to remove really like infinitely. We have infinitely like point in P1, in P3, no, sorry, in P1, such that like their inverse image, it's a split curve. Okay, so here I want to give you now a sketch of the proof. Here it's gonna be our counting function. Let me explain you what are we doing. So we want to count point in projective space P1 and cross P3. So the idea is that we can do this by counting primitive vectors in Z2 cross Z4, and the meaning of 1/4 is given by the fact that like over Z we have just 2 units which are 1 and -1. So this is just basically correcting the action of the units. And this condition here is the height function. This is is the height function condition. And this is the remove of the thin set. Okay. How do we, so the strategy of the proof, it's gonna use basically the fact that we have this double fibration. The strategy basically, it's very similar to another paper of Tim and with Brown. So this is the strategy as kind of like a similar starting point of this following paper of Tim and Brown from 2019, where they wanted to count a point of Fano fivefold, and the fivefold, their fivefold was the following. So it was W high ZI square equal to 0, and this was something in P3 cross P3. And basically here, you have like a double fibration over, like you have, if you call this, I don't know, let's say Y, you have Y from P3 and P3. And here you see basically, once you fix a WY, you get like a quadric, but when you fix ZI, you get an hyperplane. So the situation, the thing is that it also had some things looked like much more symmetric than our Fano threefold. So actually the situation gets a bit easier at some point, but really the strategy, they were combining this strategy. They were like try to count different objects using the one of the two fibration, and here we're gonna do the same. So the idea is that when the point X is, we call small, namely if it's at like its height is at most b to the power 1/4, we use so the idea is to fix X, and then we fix X, we have a quadric, and then we use the circle method to count point on a quadric. Otherwise, if X is large, so if its height it's larger than 1/4 plus delta, well, we use a geometry of number argument. And basically the circle method we can basically recycle part of Tim and Brown's work, but the geometry of numbers was turns out to be completely different. Okay, I want to start with the circle method part. And to do this, basically, I want to show you the similarity and the difference with Tim's and Brown work. So here we start with a quadric, and delta is going to be the discriminant of the quadrics, and we are requiring this not to be a square. And actually, we, if A1, A2, A3, A4 are fixed, we can really count very effectively this number of points on this quadric of 8 at most b, and you're gonna get some things like a constant, which depends on A1, A2, A3, A4, plus an error term. But of course, here the problem is that our AI are gonna be something is dependent on X. X is growing with B, so we need uniformity in the error term. And basically the things is that we can really control, so we can control the error term. If what we called delta X bad is small, okay, here delta X is gonna be, as you can imagine, product of the linear form is the discriminant of the quadric when we fix x, and this is not a square. Delta bed is going to be the squareful part of it. So this is going to be a number like the product of PE exactly dividing delta x, such that is larger than 1 of p to the power e. And then if this guy is small, so if delta bed is small. But yeah, I mean, of course we need to basically detect, like we need to find a way to control, like, I mean, of course you expect that, I mean, you know, we know that these Li are not proportional. We even know that like the coefficient of any Li is coprime. So we expect actually delta x bed to be very small in general. But of course, I mean, it can be very large, and we just need to find a way to control the case when the delta bed is large. Okay, let's go back to Tim and Ed Brown work. There, you see, we add this equation here, and here basically when you fix W, you have that. I mean, this discriminant it's pretty easy. It's basically the product of all the W1, W2 to W4. And you see here it's quite simple because you know that they are a point in the projective space. So you know that basically if D is a large squareful number dividing then you can find a large squareful number dividing E. Such that E divide omega I for some I. And this is, it's very like, it's a very easy way basically to try to control the problematic W vectors. Of course, in our case, we don't have all this symmetry, so we, I mean, we need to do something else, but actually, nevertheless, we can actually try to adopt this argument here by notice the following. So you can notice that I mean, kind of the same thing is true. So if, sorry, not that. If D divides delta X with, sorry, if is a large squareful number such that D divide the discriminant of the curve, well, this implies that we can find a divisor of D large such that E divide Lix for some X, for some I, sorry. And this is due to the fact that we're taking this Li, they're not proportional. And I mean, this is really the key fact. Yeah, because Li's are not proportional. And I mean, well, I mean, and this is now something which helps you a lot, because what you can say is that basically X needs to be in the following set. So you take the vector in Z2 such that L and LIN is equal to 0 modulo E. And this is a lattice. Of discriminant E. So you see basically what you can tell, you can tell that X basically it's a point in a lattice with a very large discriminant. And this is what is it basically very similar of what the strategy it's really the same of it Brown and team, but we need to struggle a bit more because we don't have as much. It's not as direct of their cases, but basically you see, I just wanted to give you an idea of the fact that like with the circle method, in these settings, things get a bit more messier than the Fano fivefold, but still you can struggle a bit more. And you can kind of play the same game in a way. And okay, so this is it's what concern the circle method. And now let's just focus on the second part. So in this case, now we know that the height of X it's big, meaning that it's at least b to the power 1/4. I guess I forgot here a delta. Okay. And the first things we do is to split the range of Y in the adiabatic interval. And sometimes I'm gonna denote this condition here to Y tilde capital Y. And yeah, here I just want to point out that basically, since we know that X times Y squared needs to be less than B, we get also this condition of Y. Okay. So of course, in the circle method part, we use the fibration over P1. Instead, now we're gonna kind of use the fibration over P3, and namely, we're gonna use the first equation I gave to you. So we consider okay. And now we can notice a couple of things. The first things one can notice is the following, that, okay, if we denote the GCD between Q1Y and Q2Y, so what we can do here in this equation, we can basically divide both sides. We can rewrite this equation in the following way. So we can divide both sides by D, and this, is still like an equation, like an integer. Everything is an integer, and like we want to find a solution for this new equation. But now we are going to use the fact that x1, x2 needs to be coprime. So we know that x1 and x2 needs to be coprime. So this implies that, you see, x1 needs to divide Q2y over D. So and x2 needs to divide Q1y over D. But the same is true for Q2y over D and Q1 y over D, because we just take off their ZCD. So basically, this implies that if you want to, we can explicitly define x1, x2, and this is gonna be given by plus minus Q2 y over D and Q1 y over D. And yes, yeah, all right. So basically, what we can do now is the following things, that basically our counting function can be, rewritten in the following way. We can consider the divisor D, and actually we have this lower bound for, I will comment on this lower bound over D in a moment. And then we're gonna basically sum over, so you see, because for any of, okay, we can write this like the Y of sides Y, such that D is equal to the GCD of Q1 Y and Q2 Y. I mean, because for any of these basically point, we have just one unique choice for X1 and X2. So these are going to be the same things. I mean, as I was saying before, I would just want to shortly mention on this. I mean, this is due to the fact here it's where play a role. Okay. Yes. I don't want to say why, but this is really the main feature of this condition in the theorem. And now, okay, let me just let's see how we can see it. Like we can go on. Now you see that basically. So the fact that we are requiring that the D is equal to the GCD of Q1 Y, Q2 Y, basically is telling us that D is dividing Q1 and Q2 Y, and basically this is telling us that Y is a solution of the equation xy over q2y modulo d. So now the idea is that, like, to rewrite this condition here as using this like congruence condition, and yeah, let's see how we can proceed. Now I'm gonna call this equation in this way. So the idea is that to rewrite this sum in the following way. So the sum over D stays the same, and then we introduce two other piece of notation that I'm gonna explain in a moment what they are. So and then we're counting the y in lambda alpha such that y is y. So what is AD and what is lambda alpha? So AD is going to be kind of the equivalent of the projective space over Z. It's going to be like a projective variety over Z over DZ in a way, in certain sense. So basically here, this is going to be the alpha in Z over DZ4, such that we require that alpha and D are coprime. So, like, you know, they cannot divide all these the entries of alpha. No, actually, they need to be coprime with D, and such that Q1 alpha is equal to Q2 alpha equal to 0 mod D. And then we take the equivalence relation given by the action of the unit of D over Z. So this is really like kind of like something similar to a projective variety of Z over DZ. And then we take our lambda alpha is going to be a lattice. And with lattice, this is going to be, let's say, M in Z4, such that there exists a lambda in Z, such that M is equal to lambda times alpha modulo D. So basically our vector, we are like modulo D are projecting, like, let me pass this term, projective equivalent to alpha. And I mean, now why this is turned out to be the right things, because okay, we have really like effective way to compute point in a lot, because I mean, basically we reduce our original problem to just count vector in on a lattice, and so we have. Let me also say the discriminant of this lattice is turned now to be d to the power 3. So basically, if you want to, maybe I can even do copy. If you want to count this guy here, this is going to be the area of the region with its y to the power 4 divided by the discriminant. And then you have like error term, which depends on the successive minima of the lattice. So for example, we have y to the power 3 divided by s1 alpha times s2 alpha times s3 alpha, and blah, blah, blah. Then we have y over s1 alpha plus 1, where s1 alpha are the successive minima. And yeah, you see, I mean, let's just consider the main term, so this guy here, and let's plug it here. You see that basically what we are gonna do, I mean, we are summing over d letter than y to the power 4 over b times the number of these ad times y over d to the power 3. I mean, now this guy basically you can expect to be somethings of size d, and basically what you get when you perform all the summation, this is gonna contribute with b. But then I remind you that we basically divide y in dyadic interval, and this would give you basically a constant times b log b, which is very good. The problem now is given by this error term. Because you see the point of the successive minima is that we expect all of them to have the same sum. So like generically, one expects that Si alpha to be basically all of the same sides. So the thing is that, first of all, we know that these successive minima, they kind of need to give us the discriminant, and we expect all of them to be of the same size, so they should be of size d to the power 3/4. But of course, this is, I mean, again, generically, we expect this is true, but I mean, it might be that, you know, if we take special like values of alpha, I mean, this is not true anymore. And actually, this is really like the big part of the paper is to show actually to actually show that this is true. Actually, that like generically, on average, all these lattices are well shaped, and so all the successive minima have the same size. And once you have this, and you try to basically plugs all these things in your error term, you get really sum is negligible. If this is true. Where for this, I mean, and yep, I think I stop here. Thank you for your attention.
Okay, thank you. So I will open for questions. Anybody in the audience have one? Don't feel shy. Okay, so I guess at this point, I mean, you stopped at the point exactly where people want to ask for more. So there's a natural question: how you proved that
Ah,
these
okay.
are genetically true?
I mean, I don't know if you. I mean, if you would have seen the paper, you would be happy that I stopped here. Because now I mean, it's kind of cute because I mean, basically, I don't know. I mean, actually, I mean, this problem of like finding the successive minima reduces to find basically a point in the same quadrics, in the same family of quadrics, where basically we are shortening, like, how do we say? So basically, we reduce to the fact of, I mean, basically we reduce this problem to the circle method problem. Like, basically we, the idea is that we need to find solutions, so find of let's say of the equation where x, I mean, basically we have this new variable, but this new variable has, it's very short. And so basically we can like apply the circle method part again. Like just the upper bounds are, because it's very complicated, the paper, we need like first lower bound before computing asymptotic. But yeah, it really, it worked like this. Basically you can, I mean, if you're looking for this successive minima and you like write down carefully what you're trying to do, it turns out that you basically are trying to find point again on your final variety, but where you take, instead of your original variable x, you're taking this x prime, and now x prime it's considerably shorter of the original x, and so basically you fall again in the circle method part, and therefore there you kind of like have all the strength of the circle method bound, and then you get away with that.
Okay. Like how small is that? Like x to the epsilon, like y to the epsilon, or sorry, b
No,
to the
actually,
epsilon?
I think it was like, I mean, also because you change also this y prime, like you don't have like, sorry, yeah, also
right.
this.
You don't have to be precise. My question was just like, is it small, like a lower order, lower power of b, or like really negligible?
No. It's basically, let's say that, you know, now you have that this x prime times y prime have size d, basically, where d is the discriminant, and now the thing is that your x, sorry, this is square, and then your x is less than d to the power 1/4.
Okay, so
which
yeah,
is
right.
yeah, which is exactly this range here.
Okay.
Yeah, more or less, like roughly speaking, yeah.
Right. Okay. So, but like, what's the hardest part to do? Is it to show that this will to show that it is equivalent, or like related to finding solutions to this equation, or it's harder to show the upper bound?
I mean, the thing is that you mean for this successive minima part, or
Yes.
yeah, I mean, I think it's, I mean, because I'm like, it's very technical. I'm like putting under the carpet a lot of things. I mean, of course, the problem is not exactly this one.
All right.
because the problem is that your, for example, your xi could not, they might not be, and also the yi, they could not be coprime, and this adds some extra difficulties. And yeah, and it's quite messy. Like,
Yeah,
it's
okay.
you need to be very careful about everything step you're doing, because because at the end I mean in the error term we just save, I think, a square root of log or something like this, so respect to the main term. So when the saving is, I mean, we really need a lot of and other things I can say is that here I kind of, I mean, if you see these two range I wrote down, I mean, I say when x is less than 1 to the power 4th, and then I say when x is larger than 1/4 plus delta. But of course, I mean, there is like a very, very tiny part in between. For that, we could not prove, I mean, in this range, we cannot prove any asymptotic formula. But in this range, we just have like the upper bound of the right order of magnitude, and then taking delta very small, everything works nicely. But yeah, just to give an idea of the thing that it's
right. Fair. So, well,
okay.
I'll ask. Anybody else have a question? I guess people are shy. Okay, if not, I'll say we thank Dante again. I will take with yeah, I'll take like this. Well, let me stop the recording.